this is lecture number 6, and we're talking in this lecture about linear algebra. So here we are in this part of our unit. We're talking about linear algebra. It's part of our background tools. So in the beginning, basically, a linear equation is an equation of this form where you have some unknowns, for example, x1 through xn, and they're weighted by some coefficients a1 through an, and so this is a linear combination, and that is equal to something. So this is an equation. A solution to this equation is an assignment of values to the x's that makes the equation true. And so you can have a whole system of equations, that is a whole set of equations. So in this case you can have n unknowns, x1 through xn, and m equations. Okay, and so here the way it's written, the a's have subscripts. So the first subscript refers to the row, the second subscript refers to the column. Okay, so we have m equations, and so each of these equations, each of these terms, each of these linear combinations is equal to some number. So this is an example. We can, by appropriate definition of multiplication, write this in this way. Okay, so we have now a matrix of coefficients, and based on the definition of multiplication, we call this array of numbers A, and this x and this y, we can say ax is equal to y. So we have a linear equation, a matrix equation. So again, a solution to a system of equations is an assignment of the values to the variables that satisfy the equations in the system. If a system of equations has at least one solution, we say it is consistent. If the system of equations does not have any solutions, we say it is inconsistent. So for example, here I have these two equations. Notice that these two are similar to one another. And so you can go through and show that this set of equations is consistent. That is, if I let x1 equal 1, x2 equal 1, then so 2 plus 3 is equal to 5. That's true. Minus 2 plus 3 is equal to 1. That's also true. So this is a consistent set of equations. Now so notice here, this set of equations is very similar to this set of equations, except I have a minus sign here. Now that minus sign is significant because now this quantity, if I multiply by minus 1, I get this quantity. But this is not equal to minus 1 times that. So this is an inconsistent set of equations. So we look at this equation, and we notice this equation, if we multiply it by minus 3, we get this equation. So even though we have two equations and two unknowns, really the two equations are very similar to one another. I mean, they're basically identical. So how many solutions does this system of equation have? Well, it turns out it actually has an infinite number of solutions. So a system of equation may have no solutions, in which case it's inconsistent. It may have one solution, that is a unique solution, or it may have an infinite number of solutions. Those are the possibilities. So when we talk about a matrix, we're talking about a rectangular array of elements. The matrix element is an entry in that array specified by row and column. The dimension of the matrix is the size of the array. A square matrix is a matrix with equal numbers of rows and columns. You can have a column matrix or vector. It's a matrix with only one column. Okay? In this case, this is a matrix of dimension 3 by 1. So this is basically math notation that says this vector is in the set of vectors of real values of dimension 3 by 1. You could also have a matrix or a vector of complex values, or polynomials, or other things. A row matrix or vector is a matrix with only one row. So in this case, we actually have a complex element here. So even though these two numbers are not necessarily complex, because we have a complex number in this matrix, this whole matrix is considered to be a complex matrix. A diagonal matrix is a matrix with all elements 0 except possibly on the diagonal. So A11, A22, A33, the diagonal elements are possibly not zero. They actually could be 0. One or more of these could be 0, and it's still a diagonal matrix. So this is a diagonal matrix. This is a diagonal matrix. Notice here, this matrix, it's the non-zero elements go on the what's called the anti-diagonal. So this is not a diagonal matrix. This is an anti-diagonal matrix. A special case of diagonal matrices is the identity matrix. And we're going to see that the identity matrix is basically referred to as a multiplicative identity for a particular type of matrix multiplication. So we're going to see that. Sometimes it's specified by its dimension. So this is a 3 by 3. So it's a square matrix with ones along the diagonal. And so this is an identity of dimension 2 by 2. This is an identity of 3 by 3. A null matrix or a zero matrix is a matrix of all zeros. Okay, so sometimes it's often just written as a 0. We can partition matrix, that is, we can chop it up into pieces. Okay, so here I have a matrix and I can break it up into 4 pieces. A1, A2, A3, and A4. So here are those parts, and there are certain things you can do with partition matrices. Sometimes it's convenient to leave things partitioned so that when you do certain multiplications or additions, you preserve some of the structure of the overall system. Equality: 2 n by n matrices are equal if they have the same size and if their corresponding elements are equal. Okay, so here the ijth element of A is equal to the ijth element of B. Okay, so if this is true for all I and j, that is, if every element, then we can say these two matrices are equal. Another way of saying this is if I take the matrix A and subtract B, I get a 0 matrix. So now, matrix operations. So when it comes to the basics of matrices, if matrices A and B are of the same dimension, then the sum is an element by element sum. I take the first upper corner element, I add it the corner element of the next matrix, and I get the result goes into the resultant matrix is the same size and shape of the two matrices, and the corresponding elements add. So the ijth element of the matrix C, which is the sum, is equal to the sum of the ijth elements of A and B. Similarly, subtraction is very similar, except instead of adding, you subtract. Okay, so A is equal to B if and only if A minus B is equal to 0. So that's an important thing. So here's an example. Suppose we have this matrix and we want to add this matrix. What's the result? Well, so I can add this element and that element. I can add this element and that element. But when I come to this element, there's not a corresponding element to add. So I cannot add these two matrices. The matrices have to be of the same dimension in order to do the addition. Here I have a matrix, and I have this matrix. When I add them, I get 0. So the fact that I can add two things together and get 0 means this matrix is the additive inverse of that. Or another way of saying it, it's the negative. So addition and subtraction also apply to partition matrices. So if I have a matrix that's partitioned, broken up into pieces, and I have another matrix that's broken up into pieces, I can add the pieces together. So that's a convenient thing, or subtract. As long as the pieces are compatibly defined, that is, if A1 has the same size and shape as B1 and so forth, I can define addition that way, and subtraction. So when it comes to matrices, we have these basic properties of matrix addition and subtraction. That is, first of all, it's commutative. It doesn't matter which order I put them in, I get the same sum. It's associative, and in other words, it doesn't matter if I add these two together first and then add that one, or add these two together first and add that one. It doesn't matter which order I add them in. The additive null matrix, if I have a 0 matrix the same size as A, it commutes with A and also in addition, and I just get A back. So the additive inverse is the negative of the matrix, such that when I add the two, I get 0. If I have a scalar and I multiply by the sum of two matrices, I can distribute the constant into the sum. Similarly, if I have a constant, sum of constants times a matrix, I can distribute that sum. So those are some properties of matrices. Here's some more properties. If A plus B is equal to A plus C, then we must have B equals C. Okay, so sometimes that's a kind of handy way of proving that B is equal to C. If alpha times A and A times B, A and little a times B, if they're equal, and A is not 0, then that means A must be equal to B. So it's like some of this seems like really intuitive, but because of the fact we're working with matrices, these are not just numbers. It's not trivial, but it's not that complicated either. If A times A and little a times big A is equal to little b times big A, and the matrix A is not 0, that is, there's at least one non-zero element, then we must have little a is equal to little b. Okay, so we have these various properties. So when it comes to matrices, our matrix can be a function, the elements of the matrix can be a function of some variable. Okay, and so if that's the case, we can define the differential of the matrix with respect to the variable. So for example, time. So again, it follows the definition of differentiation. The limit as delta t goes to 0 of 1 over delta t, a of t plus delta t minus a of t. So again, this subtraction is well defined in terms of matrices. And so we basically differentiate the matrix element by element. So we can talk about differentiation of a matrix and its element by element differentiation. Similarly with integration, we integrate a matrix over some interval that gives us element by element integration. So now there are some important matrix properties or functions, and in particular we can talk about multiplication by a scalar. So if I have a scalar times a matrix, basically what happens is every element is multiplied by that scalar. Okay, so for example, if I have this matrix multiplied by 3, that basically multiplies every element by 3. So that's the basic property of scalar multiplication. There are actually several different types of matrix multiplication. Scalar multiplication is one of them. Multiplication of vectors is sometimes referred to as the dot product. So if I have a row times a column, and I have the same number of elements in the row as the column, then the product of these two is actually defined this way. The row times the column is basically an element by element multiplication and then a summing. So I look at it this way. I have let's see, a row times a column, and the elements are the same elements, and I basically multiply the elements by each other and then add them. Okay, so that's my hand waving definition of how to do this kind of vector multiplication. So if you see what's happening, a1 times b1, and then you go all the way down the line until you get to an times bn. So that is vector multiplication. And now we can talk about full-blown matrix multiplication. Again, it's based on the vector product. It requires compatibly defined matrices. That is, the number of columns of the left matrix must equal the number of columns in the left matrix must be equal to the number of rows of the right matrix. So that basically means that the number of columns over here means that every row has a certain number of elements, and the number of rows over here means that every column has the same number of elements. Okay, so that the row by the column still makes sense. Okay. So with matrix multiplication, for example, I do row times column, row times column, row times column, and I can go through and show that this is the result that I get when I multiply these rows times these columns. So notice, for example, that I take this row times this column. So minus 6 times, 6 times minus 2, 0 times 5, 4 times 3. When I add that all together, I get 12 minus 12 plus 0 plus 12, and that adds up to 0. So notice I have two vectors that are non-zero, but when I multiply them, I can get a 0. So that's an important thing we're going to come back to later. We look, for example, here I have this row times this column. So 1 times minus 17, 2 times 1, and 3 times 19. Adding that all together, I get 42. Okay, so that's the process. First row, second column. Row, that gives us the element in row 1, column 2. So we saw that addition of matrices satisfied a number of important properties. It turns out that multiplication also satisfies a number of properties. So, for example, associative. If I multiply two matrices, if I have a product of three things, I multiply the first two together. That's the same as if I multiply the second two together and then the first, or I can just look at it this way, ABC. It's distributed in that if I multiply A times the sum of B plus C, A distributes. If I have the sum of A plus B times C, the C distributes. Okay. If I have the null matrix times any matrix, I'll get the null matrix back. Okay. Notice that this null matrix, because A is not square, this null matrix, when I multiply by A, I get a 0 matrix, but it's of different dimension. Okay, so I have this. The identity matrix is such that when I multiply A by the identity, I get A back. So that's part of the reason it's called an identity. It acts like the number 1 in numbers. Okay, so I multiply the matrix A by the identity, I get the matrix back. So since the matrix A is n by m, I can multiply on the left by an identity, or I can multiply on the right by an identity. And notice that two identities are different because the matrix is not square. If the matrix is square, then we can define the integer power this way. The matrix A to the power n, is equal to the matrix A multiplied by itself n times. Notice that the matrix has to be square or this is not defined. Okay, you cannot define, the matrix A will not multiply by itself. It's not the right dimension. So this only applies when you have a square matrix. For partition matrices, we can do the same kind of thing. We can define matrix multiplication. Multiplying these together, I'm going to get this row of block, this block row times this block column. Okay, and so this is what we get when we do that. So again, sometimes it's helpful to be able to have things broken up this way, and this can reveal important structure about what's going on when we do this. An important facet of matrix multiplication is that it is not commutative. That means if I multiply them this way, that's not the same as if I multiply them in the opposite order. Okay, so here's an example. I take this row times this matrix times this matrix. When I multiply it out, I get this matrix. If I try to multiply them in the opposite order, it doesn't make sense. The dimensions are not even compatible. So clearly, this is not the case. So another important function is called the transpose. The transpose is interchanging rows and columns. The first row becomes the first column, and so forth. So it's written as A transpose or A apostrophe. So this is how MATLAB uses it. So for example, if this is the matrix A, this is the transpose of that matrix. Okay, so that first column becomes the first row, and the first row becomes the first column. So it's like that. The transpose has a number of important properties. That is, if I take a matrix transpose and transpose it again, I'll get the original matrix back. If I take the matrix multiplied by a scalar and take the transpose, I can just take the scalar out. If I have a sum that I take the transpose of, that's equal to the sum of the transposes of the matrices. if I have a product that I take the transpose of, notice I get the transpose of the individual matrices, but in the opposite order. So that's different. Some matrices, there are certain matrices that satisfy this property. The transpose of the matrix is equal to the original matrix. Such a matrix is said to be a symmetric matrix. An example of a symmetric matrix is the identity matrix. So basically, the off-diagonal elements must be equal to each other, and then the diagonal elements can be whatever, but the off-diagonal elements need to be equal to each other. For partition matrices, if I have a partition matrix and I transpose it, this is what I get. So notice I get this term transposed, this term gets transposed and goes down here, this one gets transposed and goes up there, and so forth. Now, if we have a square matrix, there are special functions that apply when you have a square matrix. So, for example, the trace. For a square matrix, the trace is the sum of the diagonal elements. Okay, so just taking the diagonal elements, the trace, sometimes written in a number of different ways, is just that sum of the diagonal elements. For the trace, we have these properties. The trace of a weighted sum of matrices A and B is equal to the weighted sum of the traces, so it satisfies a linearity property. The symmetry property, that is, if I take the trace of A transpose, that's equal to the trace of A. So remember, when you transpose, you change the rows and columns, but it turns out the diagonal elements remain in place. Commutativity, if both A and B multiply, so if I can actually multiply them, now the product in general will not be equal. Okay, AB will not be equal to BA, but it's still possible for them to multiply them by themselves. Then the trace of the product is the same regardless of which order. If they actually do multiply this way, it turns out the trace of the product is equal. So even though the product is not equal, the trace of the product is equal. So if I have a matrix, the trace of A transpose A, so that's the transpose of the matrix times A, the trace of that is the sum of the squares of all the elements of the entire matrix. So that's actually kind of a handy little deal. The sum of the squares, so I take every single element, square it, and I add them up according to rows and columns. So that's basically all the elements in the entire matrix. The trace of the identity matrix is n. And if I have any matrix, an n by n matrix, and any vector x, then x transpose x I can show is equal to the trace of A times x transpose. Okay, so this is the scalar. This is also a scalar. And remember, the trace of a product is equal to, I can change the order, and so that's how this actually comes out. So this quantity is actually a scalar, and so it is its own trace. So that's how this works. If I have a partitioned matrix, the trace of that partition matrix is the trace of the diagonal blocks. The determinant. So the important thing, the determinant has a number of important properties. So if I think of a matrix in terms of its columns, and again, this only applies for square matrices, it does not apply for other matrices. Then the determinant, so now here I've replaced the jth column with some quantity ax plus by. So x is some vector, y is some vector, and then a's and b's are some scalars. Here's a property of the determinant. That is, it satisfies this linearity property. That is, the determinant of this matrix is equal to a times the determinant of this matrix, where I have now x in here, plus b times the determinant of this matrix, where I now have y in there. So that's a property. Then there's the redundancy property. If any two columns are identical, then the determinant is 0. And we have this property. The determinant of the identity is equal to 1. So these are actually defining properties for the determinant of a matrix. That is, any function that satisfies these three properties is the determinant, and it is unique. So it's kind of interesting that you could actually define a function this way, that it satisfies this linearity property, it satisfies this redundancy property, and this unity property. So here are more properties of the determinant. If A and B are both square, then the determinant of the product is equal to the product of the determinants. If I have a scalar, and I multiply by a matrix, the determinant of that result is equal to the scalar to the power n, where this is an n by n matrix. If A and B are not square matrices, but or they could be square, but they satisfy this relationship that they are the number of rows of the first matrix is the number of columns of the second. Number of columns of the first matrix is equal to the number of rows of the second matrix. Then you can go through and show that this is the case. The determinant of I minus AB is equal to the determinant of I minus BA. So, kind of an interesting thing. And finally, the determinant of the matrix is equal to the determinant of its transpose. So, for partitioned matrices, we can go through and show that a matrix like this, the determinant of this larger matrix, is equal to the determinant of this matrix A times the determinant of this matrix B. So even regardless of what D is. Similarly, because of these zeros down here. Similarly, if I have zeros up here, then this determinant again is determinant of A times the determinant of B, regardless of whatever C is. So for some examples, a second order matrix. Okay, so I take this product and I subtract this product. Okay, for a third order matrix, this is what I get for my determinant. So I can actually use this and build up the overall determinant this way. Analytical functions of a square matrix, e to the at, for example, the exponential of a matrix can be written as its power series. The cosine and the sine can also be written in terms of their power series. So these are what I've talked about here are some very basic fundamental properties, math properties of matrices. So if you've taken a class in linear algebra, you've probably seen all of this. Now, one important function that was not talked about here, but it's very important, and we will talk about it, but it's just not in this lecture, is the concept of an inverse. So notice we've done add, subtract, and multiply, no divide. Okay, because division is a very different process. Okay, so and as you can see, even addition and subtraction and multiplication is, it kind of follows, but division is a whole nother creature. So we're going to have to come back and look at that as a separate problem. So this is Linear Algebra Basics. Thanks for watching.